So let's take a look at the first one here, and we're just going to talk about security models. The rest of this stuff will be for next week, but I found the security models very interesting. They helped me understand confidentiality, integrity, and availability. This, I think, is how this was developed, if you look at the history of it. Now, they have a lot of security models here, but the main ones that give you the main point is Bell, Biba, and Clark. And they appeared in alphabetical order. First was Bell, then came Biba, and then came Clark Wilson. And you'll see they very logically developed the modern concept of security. And we'll talk about these other models as well. So the fundamental concepts are down and up. Up is a higher degree of secrecy, a higher classification level. Down is down here. So top secret is higher than secret. And then you can talk about read and up. The simple security property is no read up, which means if you're only cleared to confidential, you're not cleared for secret, you can't read anything above your level. That's sort of obvious, that's what it means. So that's no read up. And the Bell-LaPadula model enforces this. You can't read anything at a higher level of secrecy. Writing up is okay, however. You could find something at a low level of secrecy and it could then get classified and moved up. So data from below could move up as people classify it, and that does not violate confidentiality. No write down, however. Top secret data cannot be written down to secret machines. If you want to move it to there, you would have to go through a formal process of declassification, so it's no longer top secret. So no write down is a logical property. And read down is allowed. If you have top secret, you're allowed to read lower privilege stuff. That does not violate confidentiality. The people at top secret are allowed to read everything below that level. So this is the general structure of the system we're talking about. And now we can talk about the models. However, all these models are state machines. And this is the point. You can say stuff like we just said, which sounds logical intuitively. If humans were running it, this would be a good system. But if you want to put it on a computer, you have to have strict logical rules that are enforced automatically. And so you have to have a state machine. You have a mathematical model of a system, who's allowed to get to what object, and then you consider all possible interactions, and you make sure that every possible state is secure, that you cannot get to a state that violates your security policy. That's the mathematical basis of these computer security models. And that's what all these models are doing. So the Bell-LaPadula model was the first one, developed for the Department of Defense, and at that time all they thought about was confidentiality. So they just had those two rules, no read up and no write down. So the low security people cannot read the high security stuff, and the high security material cannot be written down to a low security level. So those are the two policies which would seem to preserve confidentiality. You look troubled by them. Yeah?
Yeah, because the first rule applies to people and the second rule applies to material.
No, they both apply to everything. The people have a rating and the material has a rating.
But people who have high classification can write unclassified things.
Yes, but they can't move something from a high level to a low. That's what it means. Yeah.
People can write down. It's just things that are
Yeah.
classified.
Well, you could create something that is not classified, but nothing that is top secret can be copied into the other container.
So the classification of people and documents is not in sync.
Yeah, it's easiest to think of.
That's something that is not conveyed explicitly in this description of the model.
Yes, you're right.
Programming it.
Yeah,
I would be raising alarm bells.
Yeah, okay, you're right. So, but that's what it means. It means you can't take a file and copy it onto a machine at a lower level. That's what I'm referring to here. It's a very good point. All right, so this maintains confidentiality. That's the point of it. The top secret stuff cannot be moved to a lower level, and nobody at a lower level can read it. But it doesn't give you integrity, this is what they discovered here. A low clearance operative could submit false data which moves up. Nothing prevents unauthorized alteration of high-level data. This is write up. Write up is not forbidden. So you could contaminate the secret data without secret clearance, and that's a problem. And this is where they begin to understand that there's more than just confidentiality to security. So another property you might like is the tranquility property. This means security labels don't change while the model is operating, or in the weak tranquility, it means if security labels do change, they don't ever violate your security policy. And that's what we were talking about. Conditions under which something would move from one level to another would have the weak tranquility property if they still preserve your security policy. All right, then there's a lattice-based access control is another model to try to improve this, where you subjects and objects have various classifications, and subjects have a least upper bound and a greatest lower bound of access. So the highest level of access can do alpha, beta, and gamma, but you could be cleared for only part of this. So you have system, this is the lattice. Alpha, beta, gamma has everything. This person has no privileges at all. These people have only one of the privileges. These people have two of the privileges. And the information can flow from system to system this way, and each person has different levels of access. That's the lattice system. But the BIBA model is the next one that really is a fundamental step up. This is the opposite of the Bell model. No read down means the high level data cannot read any lower level data. And no write up means no low level data can be moved up. So the point of this is you maintain integrity. No, the people at the high level can only read the high level stuff, and they cannot contaminate with any low level information getting in there. That's the idea. And this reminds me of like the Catholic Church. You have no confidentiality. You have this thing at the top called the Bible, and nobody can ever change it. And therefore you have integrity. That document never changes. But you have no confidentiality. That's the problem. This gives you integrity, but you don't have confidentiality. There is no prevent on reading up. So the low-level people can read the high-level data, and so you haven't protected the confidentiality of the high-level data. What you have protected is the integrity of the high-level data in this model. So the Bell model was too extreme because it was all confidentiality and no integrity. The BIBA model is too extreme because it's all integrity and no confidentiality, and that's when you finally realize you can't have everything and you have to have a compromise. And that's the Clark-Wilson model. The Clark-Wilson model is the more realistic one we really use, where you have limitations and you have some mixture of confidentiality and integrity. So you have these concepts of well-formed transactions and separation of duties. So you have unconstrained data items, which are things that are coming in like untrusted user input, and you have a special transaction that turns them into constrained data items that now obey your security model. So you have some process of taking data and then classifying it and assigning it to the right box. Now it's in your model. And then you have transaction procedures, and your transactions are well-formed so that they do not violate your security model. All possible transactions of moving data from here to there, make a record and maintain integrity, and don't violate your security model. And this is what you have in, say, a modern Windows system or domain controller. Another issue is separation of duties. If one department collects money and another department issues payments, neither of them is authorized to initiate purchase orders. This is the sort of thing you do. That's why you have several stages of approval for doing something important like spending money, so that no one person can commit fraud. They would have to have a conspiracy of 2 or more people to commit fraud. That's the idea. So those are the first few models, and that's, I think, as far as I wanted to go today. Let's do a Kahoot about that stuff. This is 125.3a. All right, good. I'll wait a few more seconds because there were 12 last time. Might be some more coming in. Well, I guess not. All right. All right, so which model gives you confidentiality but not integrity? The time order of them was alphabetical, so Bell was the first one which did that. All right, which model uses alpha, beta, gamma? That's the lattice model. All right. And which model has no read up? That's the Bell model. That gives confidentiality. The people with secret clearance cannot read the top secret stuff. So that's the Bell model. And which model enforces no read down? That's the Biba model, the opposite of the Bell model. All right. That's faces, all right. I think that person doesn't really care about points. And Emmanuel is here. Good. And Muhammad. Good. All right. So, that's it for the lecture for 125. And there is no hands-on for 125, so I'm just going to answer any questions